Hey everybody, Dr. White here with some solutions to some of the problems from the Chapter 2 homework. First of all, I want to do number 4 out of section 2.1. This one's about the Binford distribution, a distribution on the numbers from 1 to 9, and the PMF is log base 10 of x plus 1 over x for each x from 1 to 9. So the first thing they wanted you to do was to verify that this was really the probability mass function for a valid random variable. So two things need to happen. On each of the possible values, the probability needs to be positive. Secondly, the sum of the values of the alleged PMF has to equal 1. So first of all, let's check and see if f of x is always positive. Well, it's log base 10 of x plus 1 over x. But x plus 1 over x is going to be 1 whenever x is a positive number like that. So a little bit more than 1. And the log base 10 of any number more than 1 is more than 0. Okay? So we're okay there. Now, secondly, do the sum of the f's equal 1? Well, when you sum the f's over the sample space, your sum in x goes from 1 to 9, log base 10 of x plus 1 over x. Well, by a property of logs, that's the log base 10 of x plus 1 minus the log base 10 of x. So if I write that sum out like this, so here's my x equals 1 term, my x equals 2 term, dot, up to the x equals 9 term, you'll see that there's some cancellation. The first term of the first part of one term will cancel with the second part of the term beyond it. And the result is that you're only going to be left with the first part of the last term and the last part of the first term. So telescoping sum here. We just got to figure out what it is. Well, log base 10 of 10 is 1 because 10 to the 1 makes 10. Log base 10 of 1 is 0 because 10 to the 0 makes 10. 1 minus 0 is 1. So sure enough, the values of the PMF sum up to 1. So it really is PMF for a random variable. Next, they wanted you to say what the CDF was. So that's capital F of x. By definition, the probability that capital X is less than or equal to x for any real number x, anywhere from minus infinity to infinity. So I first think, what if capital X is less than 1? That puts capital X less than any of the possible values of the random variable. And so the chance of your random variable being less than or equal to that would be 0. Let me do another easy one. What if x is bigger than or equal to 9? It is now bigger than all the possible values, 1 through 9, of the random variable. And so the chance of being less than or equal to x would include the chances of being 1, 2, 3, 4, 5, 6, 7, 8, and 9, adding up to 1. So it stays that way for all x bigger than or equal to 9. The tough part is the in-between, if x is at least 1 but less than 9. Well, what I'm going to focus on is really what's the value of what we call the floor of x. That's two straight bars and then like little floors on the edges around the x. The floor of x is the largest integer that is still less than or equal to x. So like the floor of 8.3 would be 8. The floor of 7.99 would be 7, and so on. And if you take any real number x in this range, then the only chances for values less than it would be the ones from 1 up to the floor of x. And so we're adding up, j goes from 1 to the floor of x, log base 10 of j plus 1 over j. So that would be a statement of the CDF, but you're probably interested in simplifying this bit right here, which you can do. Let's just come down here and let's add it up. There's the j equals 1 term. Keep on going until you get the j equals floor of x term. And actually, I'll have a mistake. That should be floor of x plus a 1. So I will fix that right here now in my PDF. and then minus just the floor of x, not the floor of x minus 1, okay? So you should be taking log of floor of x plus 1, and here you should be taking just log of floor of x, so I'm subtracting that off. And the result is that this term will stay, and that's a log of floor of x plus 1. And this term here, which is left over from here, stays, and that's a 0. And so you should have just log of floor of x plus 1 as your final answer. So I'm going to make those corrections here. Log of floor of x plus 1, quantity, floor of x plus 1, is the value if capital X, if little x is in here. Okay. Next up is number 4 from section 2.3. They say let capital X be a random variable that has a mean and a variance. Make a new random variable, capital X minus mu divided by its standard deviation. What's the expected value of this new random variable? Well, you can think of it as 1 over sigma times capital X minus mu. An expected value of a constant times a random variable is the constant times the expected value of the random variable. That's part of the linearity of expected values. Further in linearity, the expected value of a difference is the difference of expected values. So I've got expected value of x minus the expected value of the constant random variable mu. Now, another property is that the expected value of a constant random variable is that constant. And expected value of x is just mu. The mu is just a notation for the expected value of x. So this stuff here is 0. 1 over sigma times 0 makes 0. They next ask for the expected value of x minus mu squared. Notice that's actually the same as the variance of this x minus mu over sigma random variable, because the variance would be the expected value of it squared minus the square of its expected value. We've just shown its expected value is 0, so you're only getting the expected value of the square of x minus mu over sigma. So they're really asking for the variance of x minus mu over sigma shorthand when they're asking for this. Well, whatever, let's find it for them. Square in the top, square in the bottom. Linearity says I can factor out the 1 over sigma squared. It's constant. And then I'm looking at this. But wait a minute. That is exactly, well, I'm missing a parenthesis there. Let me stick the parenthesis in. There should be like a parenthesis right here to match this parenthesis right here. So let me stick that in. Here we go. And anyway, this would be exactly the definition of the variance of x, which is sigma squared, the notation for variance. Sigma squared over sigma squared is 1. So, take a random variable that has a mean and a variance, subtract off its mean, and divide by standard deviation. You get a random variable whose mean is 0 and whose variance is 1. That's pretty useful for later on. Number 18 in this section, I'll go ahead and grab the book and read it out for you. 2.3, number 18. Yeah, let x have a geometric distribution, and we got to show that this conditional probability is equal to this, all right? That's the problem we have. So I'm saying, let's let x be geometric with some parameter p, where p is the chance of success on each trial in your Bernoulli process, okay? So p is a number between 0 and 1. Before we get started on solving this problem, notice the important, interesting, useful fact about geometric random variables. The chance that a geometric is bigger than some number little x is the chance that your first x trials are all failures. So you would, the chance you have to wait more than X trials for a success is the chance that the first X trials are all failures. So that's a 1 minus p chance of failure raised to the X power. Super useful little fact about geometrics. Why is it so useful? Well, we'll see one reason here. So we got looking for this conditional probability, which is basically saying, say you're waiting for a success, and like you've already waited K or more steps, okay? You've waited K or more trials, and you have not seen your success yet. So you know that capital X is going to have to be bigger than K. You've been waiting K, you haven't seen it. Capital X is bigger than K. Given that, what is the chance that it's bigger than K plus J? Which is saying, like, what's the chance I'm going to have to weigh more than another J tries for my success? Well, by definition of conditional probability, that's the probability of the A and B over the probability of the B. And when I look at this and here, being bigger than K and being bigger than K plus J means I just got to be bigger than the bigger of those two numbers, which is K plus J. So the top's a little simpler. And now we'll use this fact here. First of all, when the X is K plus J, and second of all, when the X is K. And now I can use property of exponents to say this is 1 minus p raised to the K plus J minus the K power, leaving a J, which, by this fact, is exactly the probability that X is bigger than J. So this is saying, if you've waited K tries and you still haven't seen your success, it's just as if you'd started it from the very beginning. The chance you got to wait more than another J tries is just the same as the chance at the beginning that you'd have to use more than J tries to see a success. So it's like the process has no memory. A Bernoulli process has no memory. What happens on the previous trials has no effect on what happens on future trials. The fact that you haven't had your success yet does not affect what happens in the future. It's still geometric going forward in terms of waiting for that first success. That's basically what's going on here. Super useful, interesting fact. We call this the memoryless property of the geometric random variables. Next up, section 2.4, number 18. So let me read that one out so you can remind all of us of what it was. So there's a group of people and they're testing for a certain disease. And a blood sample gets taken from each of N individuals, and part of each sample gets placed in a common pool, and the common pool has been tested. So you're only doing the one test right now on this mix of the blood from the N people. And if the result's negative, then you figure there's nobody had the disease, and you just stop there with the one test. But if the result of the test on this mixed blood sample was positive, then you figure, at least one of those people that we mixed up here must have the disease, so we better test each of those people, okay? And so you're either going to test you're either going to do one test, or you're going to do one test plus N tests, one on each of the individual people. Okay, now suppose that the chance is 0.05 for any given person to have the disease. You pick a person at random from the population, 5% chance they got the disease, independently of all other people. And say that there's 5 people you need to be looking at, okay? Then what is the expected number of tests needed? So I am first going to find the chance that there's only one test needed. That's the chance that none of those 5 people have that disease, and that would be a 95% raised to the 5th power, okay? On the other hand, what's the chance that you need to do 5 more tests, one on each of the people, for a total of 6 tests? Well, that would be 1 minus the chance that you don't need to do the extra test. So that's 1 minus the chance that you've already figured out. 1 minus 0.95 to the fifth. So if you think of it in terms of a random variable where x is the number of tests needed, the probability mass function for x can be written with this little table here. 2 possible values, 1 and 6. Chances given like that. So the expected value is the sum of the possible values times the chance of, the 1 times the 0.95 to the 5, plus the 6 times the 1 minus 0.95 to the 5. And some people took calculators out and they claim to have found that it was 2.13, and I'll go with that. Anyway, this is fine as a final answer. You don't have to simplify if you don't want. How about number 4 from the section on Poisson random variables? And so this is a cool problem. X is a Poisson random variable with a rate lambda. I've left off a closing parenthesis there, so let me just add that on. Okay. So it should be a closing parenthesis here to match this opening parenthesis. Well, anyway, we don't know the lambda. We're told, though, that 3 times the chance that x is 1 is equal to the chance that x is 2. And just off of that, find the chance that x is 4. So I set up an equation representing this. I know the chance that x is 1 would be lambda to the 1, e to the minus lambda over 1 factorial. The chance that x is 2 would be lambda to the 2, e to the minus lambda over 2 factorial. Memorize your PMFs for all your basic random variables, including the Poisson. And so I got this equation, and I think I could solve it for lambda. 1 factorial is 1, 2 factorial is 2, lambda to the 1 is just a lambda. And look at this equation here. I can cancel an e to the lambda, e to the minus lambda from both sides. I can cancel a lambda from both sides. I can multiply both sides by 2, and I get lambda is 6. So the chance that x is 4 is lambda to the 4, e to the minus lambda over 4 factorial, and you're done. Woo! So that's all I've got for you here. Sorry about all those typos, but they will be fixed in the PDF that you can snatch off of Canvas. So bye-bye.